Welcome to our comprehensive guide on number systems and codes. In the digital world, understanding how numbers are represented and manipulated is crucial. Today, we'll explore the basics of number systems, their conversions, and the special codes used in computing. Whether you're a student or just curious about how computers handle numbers, this video will break down complex concepts into easy-to-understand segments. Let's start by understanding what a number system is and why it's so important in digital electronics and computer science. Number system is a way to represent numbers using a specific set of symbols or digits. In everyday life, we use the decimal system, which is based on 10 digits from 0 to 9. However, computers use other systems like binary, octal, and hexadecimal. Each system has its own base or radix, which determines how numbers are constructed. Understanding these systems is the foundation for working with digital devices and programming languages. Let's begin with the decimal system, which is the most familiar to us. It uses 10 digits from 0 to 9 and is based on powers of 10. Each position in a decimal number represents a different power of 10, making it easy to perform arithmetic operations. This system is used in our daily lives for counting, measuring, and calculations. However, computers find it more efficient to use other systems, which we'll discuss next. Binary system is the backbone of all digital electronics. It uses only two digits, 0 and 1. Each digit in a binary number is called a bit. Computers use binary because it's easy to represent two states on and off or true and false. Every operation inside a computer, from calculations to data storage, relies on binary numbers. Let's see how binary numbers are structured and why they're so essential. Octal system is another way to represent numbers, using 8 digits from 0 to 7. It's less common than binary or decimal, but is sometimes used in computing for compact representation of binary numbers. Each octal digit corresponds to 3 binary digits, making conversions straightforward. Octal numbers are often used in programming, especially in older computer systems and digital electronics. Hexadecimal system, or hex, uses 16 symbols, 0, 9, and AF. It's widely used in computing because it can represent large binary numbers in a compact form. Each hex digit stands for 4 binary digits, making it easy to read and write binary data. Programmers and engineers often use hexadecimal to simplify complex binary codes, especially in memory addresses and color codes. You might wonder why we need so many number systems. Each system serves a unique purpose. Binary is perfect for computers, octal and hexadecimal make binary easier for humans to read, and decimal is best for everyday use. By understanding these systems, we can bridge the gap between human logic and machine operations, making programming and digital design more efficient. Let's learn how to convert decimal numbers to binary. The process involves dividing the decimal number by 2 repeatedly and recording the remainders. These remainders, read in reverse order, form the binary equivalent. This method is fundamental in digital electronics and programming, as it helps translate human-readable numbers into machine language. To convert a binary number to decimal, multiply each bit by 2 raised to its position power, starting from the rightmost bit. Then sum all the results. This process allows us to interpret binary data in a form that's meaningful to humans, bridging the gap between machine and human understanding. Converting decimal numbers to octal involves dividing the number by 8 repeatedly and recording the remainders. Just like with binary, the octal equivalent is formed by reading the remainders in reverse order. This conversion is useful in digital systems where octal representation is preferred for simplicity. To convert an octal number to decimal, multiply each digit by 8 raised to its position power, starting from the right. Add up all the products to get the decimal value. This method is straightforward and helps in interpreting octal data in a more familiar decimal format. Decimal to hexadecimal conversion is similar to other conversions. Divide the decimal number by 16 repeatedly, recording the remainders. The hexadecimal value is obtained by reading these remainders in reverse. Hexadecimal is especially useful for representing large binary numbers compactly. To convert a hexadecimal number to decimal, multiply each digit by 16 raised to its position power, starting from the right. Add up all the products to get the decimal equivalent. This process is essential for understanding memory addresses and color codes in computing. Binary numbers can be easily converted to octal by grouping the binary digits into sets of 3, starting from the right. Each group is then replaced by its octal equivalent. This method simplifies the representation of long binary numbers, making them easier to read and write. To convert octal numbers to binary, replace each octal digit with its 3-digit binary equivalent. This direct mapping makes the conversion process quick and efficient, especially in digital electronics where both systems are used. Binary to hexadecimal conversion involves grouping binary digits into sets of 4, starting from the right. Each group is then replaced by its hexadecimal equivalent. This method is widely used in programming and digital design for its simplicity and efficiency. To convert hexadecimal numbers to binary, replace each hex digit with its 4-digit binary equivalent. This conversion is straightforward and helps in interpreting hexadecimal data in binary form, which is essential for low-level programming. Binary addition is similar to decimal addition but uses only 2 digits. The rules are simple: 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, and 1 plus 1 equals 10. When the sum exceeds 1, a carry is generated. Binary addition is fundamental in computer operations, forming the basis for more complex arithmetic. Binary subtraction follows rules similar to decimal subtraction. The key difference is borrowing, which occurs when subtracting a larger digit from a smaller one. The rules are 0, 1-0 equals 1, 1, 1 equals 0, and -1 equals 1 with a borrow. Mastering binary subtraction is essential for digital circuit design. Binary multiplication is straightforward, using only 0 and 1. The rules are 0 times 0 equals 0, 0 times 1 equals 0, 1 times 0 equals 0, and 1 times 1 equals 1. Multiplication in binary is similar to decimal, but much simpler due to the limited digits. This operation is used in computer processors for calculations and data processing. Binary division is similar to decimal division but uses only 2 digits. The process involves repeated subtraction and is used in digital circuits for arithmetic operations. Understanding binary division is important for designing efficient algorithms and hardware. In digital systems, it's important to represent both positive and negative numbers. Sign number representation allows us to do this. There are several methods including sign magnitude, ones complement, and twos complement. Each method has its own advantages and is used in different contexts within computer systems. Sign magnitude is a simple way to represent sign numbers. The leftmost bit indicates the sign, 0 for positive, 1 for negative. The remaining bits represent the magnitude. While easy to understand, this method has some drawbacks such as 2 representations for 0. Ones complement is another method for representing negative numbers. To find the ones complement, simply invert all the bits of the number. This method also has 2 representations for 0, but it simplifies some arithmetic operations compared to sign magnitude. Twos complement is the most widely used method for representing sign numbers in computers. To get the twos complement, invert all the bits and add 1 to the result. This method solves the problem of 2 zeros and makes arithmetic operations more efficient. Twos complement is preferred because it simplifies hardware design and arithmetic operations. With this method, addition and subtraction can be performed using the same circuitry, and there's only one representation for 0. This efficiency is why modern computers use twos complement for sign numbers. Gray code is a binary code where 2 successive values differ in only 1 bit. This property reduces errors in digital systems, especially when values change rapidly. Gray code is commonly used in rotary encoders and digital communication systems. Gray code's unique property of changing only 1 bit at a time makes it ideal for minimizing errors during transitions. It's widely used in hardware devices like rotary encoders, where precise position detection is crucial. Gray code also finds applications in error correction and digital communication. Access3 code is a non-weighted code used to express decimal numbers. Each decimal digit is represented by its binary equivalent +3. This code is self-complementary, making it useful for error detection and simplifying certain arithmetic operations. Access3 code is often used in digital systems for error detection and simplifying the design of arithmetic circuits. Its self-complementary nature makes it easy to generate the nines complement of a decimal number, which is useful in subtraction operations. BCD, or binary-coded decimal, is a code where each decimal digit is represented by its own binary sequence. This makes it easy to display decimal numbers on digital devices like calculators and digital clocks. BCD is widely used in applications where decimal accuracy is important. BCD code is especially useful in devices that require precise decimal representation, such as calculators, digital clocks, and financial systems. By representing each decimal digit separately, BCD avoids rounding errors that can occur with pure binary representation. ASCII stands for American Standard Code for Information Interchange. It's a character encoding standard that represents text in computers. Each character, including letters, numbers, and symbols, is assigned a unique binary code, allowing computers to store and communicate text efficiently. ASCII code is fundamental to digital communication. It allows computers and devices to exchange text data reliably. From emails to programming languages, ASCII ensures that text is represented and understood consistently across different platforms. Error detection is crucial in digital systems to ensure data integrity. Various codes are used to detect and correct errors that may occur during data transmission or storage. Let's explore some common error detection and correction codes used in computing. Parity bit is a simple error detection code added to data. It can be even or odd parity depending on whether the total number of ones should be even or odd. Parity bits are widely used in memory systems and communication protocols to detect single-bit errors. While parity bits are useful for detecting single-bit errors, they cannot detect all types of errors, such as when 2 bits are flipped. For more robust error detection and correction, more advanced codes are needed, like the Hamming code. Hamming code is an error-correcting code that can detect and correct single-bit errors. It uses multiple parity bits placed at specific positions in the data. Hamming code is widely used in memory systems and digital communication to ensure data reliability. Hamming code works by adding extra parity bits to the data, which are calculated based on specific positions. When data is received, the system checks these parity bits to identify and correct any single-bit errors. This process greatly improves data integrity in digital systems. Besides parity and Hamming codes, there are many other error detection and correction codes such as CRC and Reed-Solomon codes. These codes are used in various applications from data storage to wireless communication to ensure data is transmitted accurately. We've covered the basics of number systems: decimal, binary, octal, and hexadecimal. Each system has its own strengths and is used in different areas of computing. Understanding these systems is essential for anyone working with digital technology. We also explored various codes like Gray, XS3, BCD, and ASCII. Each code serves a specific purpose, from simplifying arithmetic to enabling text communication. Mastery of these codes is vital for digital design and programming. Error detection and correction codes are essential for reliable digital communication and storage. They help maintain data integrity and prevent data loss, making them a cornerstone of modern computing systems. Number systems and codes are not just theoretical, they have real-world applications. From programming and networking to digital electronics and data storage, these concepts are used every day to make technology work seamlessly. Congratulations! You've learned the fundamentals of number systems and codes, including their conversions, arithmetic, and error detection methods. With this knowledge, you're better equipped to understand how computers process and protect data. Keep exploring these concepts to deepen your understanding and apply them in your studies or career.